Hello everyone, we are Southern Cross Innovations and we are here to present our blueprint for the engineering, economics and ethics of a Martian city-state. So we are a team of young Australian professionals with a passion for technology and for Mars. My name is Caleb and I'm joined by a few members of our team here today, Alex, Tim, Rob and Tom, as we take you through our technical design, the economics and the political, social and cultural aspects that we propose for a Martian city-state. Firstly, our resources. Our resource production methods are similar to what we proposed last year. We have categorized our resources into the strategic resources and general resources. The strategic ones we believe will be more difficult to acquire. These are the ones where we will need to find deposits: water, copper, thorium. Tim and Alex will discuss these in more detail later. The general resources are those which are more easily sourced from the air and the regolith. These will be the main ingredients for our bulk goods like brick, steel, and oxygen. From the Martian air, we'll be able to process that air by filtering out the dust and using compressors and coolers to separate out the individual elements. The regolith itself we'll be able to gather with 5-ton harvesters, with about 45 of these harvesters being required in the long run in order to meet our production targets. Now, this would be considered a modest mining operation here in Australia, and so we believe this would be quite feasible. The regolith, once gathered, would be crushed and then separated with traditional gravity, magnetic, and electrostatic methods. Once we have our individual streams of materials separated out, these resources are then able to be combined in our 5 main works facilities, which we've collectively called the manufactorum. The alchemy works would be where we combine the air and water to make oxygen, rocket fuel, plastics, and various chemicals. The earthworks would combine the regolith and water to make compressed bricks, fertilizers and soils and carbon products. Our steel and glass works, well, they're fairly self-explanatory. And our vault works would be where we manufacture aluminium and magnesium products. Now, all of these processes are going to require some amount of power, particularly our alchemy and our vault works. Now, we've estimated that our total power consumption for all of this industry would be about 1 gigawatt in total, and that the city itself would also require about 1.5 gigawatts for day-to-day living purposes. So where do we propose getting all of this power? We propose using thorium molten salt reactors. Now, these will feed traditional steam turbines, as those are easy to build and maintain with traditional technologies. And the peaks and troughs of energy use and generation will be handled with a molten silicon thermal energy storage system. Now, this is a technology that has shown fantastic promise lately, in that the silicon itself glows very brilliantly at high temperature, and that energy can not only be reclaimed with heat exchangers, but we can reclaim it with thermovoltaic panels, which are extremely high efficiency also. Now, all of these power systems would be distributed around our city in order to ensure that the supply remains uninterrupted. We would have redundant systems, and the excess heat from all of these could be piped through the city in order to provide warmth. So the city itself, it'll be comprised of habitat structures, which we have fondly named our Colosseums, for obvious reasons by this picture. Now, these can be built anywhere so that we can site them near resource deposits. These will be multi-purpose steel vessels that are reinforced with brick walls. They'll be about 180 meters in diameter, and the pressure will be half of that of a normal Earth atmosphere in order to reduce our overall material requirements. In order to keep things comfortable for aspiration, we'll be adding a little bit of additional oxygen. Inside each of these, we'll be able to house up to 1,000 citizens with a generous 45 square meters of living space per person. We'll be able to excavate them deeper if we need rail stations and storage for them, and we can isolate each one of them in the event of an emergency. The domed sections over each habitat will feature some green space for luxury crops or views of the stars, and the 2-meter deep soil layer and steel that supports that soil would shield those core living areas below from radiation events. In terms of what these might look like, well, the internal architecture would have a lot of brick and steel facades, but we could spice this up with imitation wood panels from aluminium, and the spacious volumes and atriums would help to alleviate any indoor feelings. If we zoom out a little bit, we can see how these might fit together. So here we've had the very rare opportunity to actually plan an entire city from the very beginning. And this will be essential because the main issue with city planning today is typically traffic. Cars, pedestrians, cyclists, everyone is fighting over the streets and that street level. We even have to cross the street when we go from one building to the next in a modern city. Our Colosseums, however, will feature numerous transport layers. We'll have subterranean trains and trams, the red and blue lines seen here, to local neighbourhood connections and elevated scenic avenues at the dome level. The city workplaces and commerce hubs would be decentralised, located throughout the city on these key transport lines, which would reduce the average commute and create what we call super blocks of quieter residential neighbourhoods where walking and cycling home is easy and where children can play. Some of these colosseums, they could even be dedicated entirely to green space and parkland. Others could be inner city hubs for light industries, those industries that are considered quiet and clean enough for in the city. And all of these options, well, they'd combine together to make our city an enjoyable place to not just work, but to live in close proximity with one another. As we zoom out once more, we can see our compact city here in blue, approximately 40 habitats across. The resource processing and heavy industry, the works facilities would be located in separate clusters of habitat structures so that we can have surface vehicle access and to keep noise pollution and other pollution away from the main city. Our farms, seen here in green, are just a couple kilometres away, which leaves us with ample space to grow the city in the future. All of these systems will be connected by long-distance heavy haul rail, which my colleague Alex will talk about now.
Thank you, Caleb. As Caleb has just mentioned, long-distance travel will be predominantly rail travel. This includes relatively local transport to and from the manufactorum, starports, and the greenhouse modules, as well as sites further afield, like laboratories, mines, and isolated outposts. Next slide, please. The trains will be driverless freight trains. They will be powered by methane and oxygen, as electrification of the rail network is infrastructure and maintenance intensive and will not be feasible. Otherwise, they will be fairly standard rail vehicles, similar to those already in use in Western Australia, as pictured on slide. The trains will use unpressurized hopper wagons for bulk materials, pressurized carriages for passengers, and a containerized system for other freight sensitive to the Martian atmosphere. Next slide, please. Rockets are the other long-distance transport option. The SpaceX Starship model has been used to estimate freight costs for rockets on Mars. The cost of travel is around $40 per kilogram and is relatively independent of distance. We estimate that they can deliver to anywhere on the Martian surface with a single launch. As such, trains are more economic for bulk materials over shorter distances, and rockets are better for longer distance travel, with the transition point being around 1,600 kilometers. For longer distance travel between sister city-states, rockets can be used for passenger, commercial, and specialized freight. Freight containers will need to be standardized between rail and rocket to minimize loading times at the starports. Next slide, please. I will now discuss water, one of our key strategic resources. The daily demand for water is approximately 200,000 meters cubed per day. The bulk of this demand is municipal, with the remaining 13% being used by the agricultural sector. Industrial consumption is negligible compared to the previous two consumers. After recycling, the colony has a net intake demand of 2,420 meters cubed per day. At this scale, there are only two viable sources for water. The first is the Martian hydrosphere. While evidence of the hydrosphere is growing, there is still considerable uncertainty regarding its size and suitability for water extraction. A more abundant and easier to extract source of water is ice. Surface and subsurface ice has been detected across many regions of Mars and sometimes in considerable quantities. The required net demand for water means extraction will require a medium-scale mine. At Martian temperatures, ice is hard, with a Mohs hardness of 6. As such, the best extraction method would be to use heated cutters to raise the temperature and soften the ice so that it can be rendered into chunks for transport back to the city-state for processing. This means the wear and tear on the cutters is reduced, and transport does not need to spend energy maintaining heat and pressure to the cargo. Next slide, please. Once brought to the city-state, the ice is thawed and treated by the intake reverse osmosis plants. After hardening, raw water is circulated through the agricultural sectors. Industrial water is taken from the same source but is not returned due to contamination concerns. Potable water is circulated through the city-state and returned to the wastewater treatment plants. The water grid for the city-state will need to be interwoven between colosseums, with multiple redundancies. Each colosseum should be supplied by at least 2 connections and some degree of local storage. Storage can be achieved by using internal tanks in the basement. If each colosseum has a decent-sized tank, the city-state could have up to 100 days of excess supply. Local storage will of course fluctuate depending on colosseum specialization. The treatment plants will be sited between the city-state and the agricultural sectors, as it minimizes pumping distance for each cycle. This also promotes ease of nutrients and fertilizers back to the agricultural sectors. Next slide, please. The colony will rely on a 2-stage treatment plant, which is scaled up from the 1,000 person colony. This consists of a biological nutrient removal system, which uses bacteria to break down the wastewater streams, and a combined microfiltration reverse osmosis treatment stage to bring the quality of water up to purity. The water is then hardened with calcium carbonate. Raw water for the agricultural and industrial sectors is taken off at this stage. The remainder is dosed with fluoride and chloramine to make it potable. This is a tried and tested suite of technologies used in the majority of urban wastewater treatment processes. It is more reliable and requires significantly less area than both wetlands and trickling filter technologies. This treatment process will fit a 50,000 meter cube per day plant into a single colosseum. 4 such colosseums would be required to treat the demands of the city-state, but at least 6 would be required to ensure proper redundancy for such a critical recycling process. My colleague Tim will take the presentation from here.
Thanks, Alex. So now that we've discussed water, what about food? Now, previously we proposed a vegan diet, but with the additional scale that we have with 1 million people, it's quite possible to bring some of those animal products back in. Now, does this mean that our settlers are going to be tucking into a delicious Magyu steak every other night? Unlikely. Traditional livestock just takes up too much space. However, poultry, fish, or insects that can eat the inedible portions of our crops are much more likely. Now, I know what you're thinking. Is it going to taste the same? And the answer is no. The reduced pressure impacts our sense of taste and smell, in particular the sweet and salty receptors. So the cuisine has really got to focus on the other tastes being sour, bitter, and umami. It's also going to change the cooking techniques. Water's going to boil at about 80 degrees, and that's going to increase cooking times across the board. But it's not all bad. The lower gravity means that potentially we're going to have the fluffiest soufflés ever. Martian chefs are going to have to adapt to this. We're going to get a truly unique cuisine. Next slide, please. So how are we actually going to grow all of this food? Previously, we'd advocated for artificially lit plant factories, but when you scale this up, the power consumption is just obscene. So we're going to be using the sun. This results in a greenhouse area approximately the size of Manhattan and Brooklyn combined, but this gives adequate surplus for export and also to mitigate the risk of any kind of crop failures. Food is also going to need to be stored, and the best way to do this is to distribute it across all of the habitats. Again, this avoids any single points of failure. Now, we're using the sun, and that means we're at risk of dust storms. Luckily, even the most severe dust storms still have a substantial diffuse component of light that makes it down to ground level. And we calculated this and used a thermal model of our greenhouse to calculate the maximum latitude that we can maintain a 15-degree internal temperature without any additional heating. And it turns out that this is about 40 degrees latitude with a single glazed greenhouse. Now, obviously, we can go to higher latitudes, but we might need additional heating, and it'll become seasonal. Next slide, please. So whereabouts are we actually going to be putting our settlement? This is dependent on our strategic resources, and in particular, water is at the higher latitudes, as you can see in the lower map, whereas light and the easy access to orbit is at lower latitudes. We can trade these off and get sort of a band of appropriate locations, and then look for additional resources in those locations. In particular, our selected location is about 30 degrees north and 60 degrees west. Which has access to thorium, as you can see in the upper map, water, and also, hopefully, large deposits of copper in the Tharsis and Marianas outflow channels. I'll now hand you over to Rob for our city development.
Thanks, Tim. So now that we've got our site selected and our technologies defined, we can now talk about our city's development and costs. With a basic population analysis, we've estimated that it would take approximately 60 years for our city to reach a population of 1 million people. This is primarily driven by immigration and is thus limited by our transportation technologies. Over this period of time, we estimate that 300,000 tons of equipment will need to be procured and imported to Mars, resulting in an end cost of approximately $260 billion. Next slide. So $260 billion spread across the population implies a cost of $260,000 per person to essentially buy an apartment and essentially citizenship in our city. Add in transportation costs to get to Mars, and the immigration cost will be approximately $500,000. This is financed with a simple loan, not unlike a home loan. We estimate it's paid back over 20 years with a 3% interest rate. We estimate that our colonists will be paying approximately $35,000 per year to facilitate this debt. This implies an average wage of approximately $100,000 per person, and thus a GDP of $130 billion for the entire city to allow for those wages as well as growth. Now, this may sound like a lot, but it's roughly in line with a developed Western city, for example, Brisbane, Australia. Next slide. So before we talk about potential revenue costs, we need to talk about shipping throughout the inner solar system, as this will be key. If we assume a baseline technology, in this case SpaceX's Starship, and combine that with the assumed shipping costs of $500 per kilogram Earth to Mars and $200 per kilogram Mars to Earth, we can estimate various costs to different locations throughout the inner solar system. From this, you can see that Mars has a great advantage over Earth in terms of shipping costs, it being 2 orders of magnitude cheaper to ship from Mars to Tycho Station than it is from Earth. Now, the Starship may not be well optimized for all of these locations. However, it does serve to highlight the case of Mars's advantage, and any technological advantages will also help Mars. Next slide. So based on this, our primary source of income is going to be providing services to asteroid mining. Now, asteroid mining is unlikely to be 100% automated, if for no other reason than due to light speed lag, and this creates a potentially large market for exports from Mars. We estimate approximately $75 billion can be generated annually per year. In addition to this, we'll be getting money from technological licenses, which are a bit more reliable than just purely patents. Patents can struggle to be commercialized. And as an example, Siemens makes $16 billion per year off of its digital licenses alone. Looking at the key industries involved in living on Mars, representing several $1 trillion in today's markets, and if we assume a relatively small market penetration of 2% coupled with, say, a 15% commission on those technologies, we estimate $28.5 billion can be generated annually. Next slide. So in addition to this, there are a number of other sources of income, the most interesting being tourism. Now, Mars is ill-suited for mass tourism, given that a round trip would cost somewhere between $500,000 and $1 million and take 2 years of your time. However, there would still be people willing to pay this. A better source would be asteroid miners returning from shore leave. Companies would be incentivized to encourage asteroid miners to return to Mars due to the cheap energy costs. And anyone who's done a site rotation will know that you'll tend to have a lot of income but little to spend it on when you're away. Next slide. So as we can see from this analysis, Mars is going to be heavily dependent on a solarized economy spread across the inner solar system, much like we're dependent on a globalized economy today. From our estimated GDP of 137 billion, the company will need to raise revenue in order to provide services and infrastructure. This will be done through a rent of services, progressive income tax, and a value-added tax. Now, the rent of services is important because we want to keep corporate tax rates low in order to encourage investment. Instead, money will be made from these corporations by selling electricity, water, steel, and aluminium to them. This money will then be spent for infrastructure expansion and repair costs throughout the city, a universal basic income to provide a robust safety net encouraging innovation, a public healthcare system, which will be a necessity due to the low gravity and high radiation environment, as well as a robust education program. However, the education program would be more focused on retraining rather than initial education. Next slide, please. So in order to decide where all this money goes, we've come up with a slightly different political system in order to minimize corruption. All elections will be publicly financed, with industry's voice being included through a chamber of commerce. In addition to this, there'll be a chamber of infrastructure so that maintenance staff have a direct say. And finally, everyone will be automatically registered to vote on arrival at the city, with penalties for people who don't vote, as is currently practiced in Australia. Next slide, please. So with our political structure defined, we can now start to talk about our various legal rights. Tom?
Thanks for that, Rob. As if for my colleagues, we discussed the infrastructure, the economics, as well as the political system. But alongside these considerations of the Mars City, we also need to consider that we'll need stronger communities to ensure that we have strong cohesion within the population on Mars. To ensure this, we've chosen the methodology of Oliver Wendell Holmes, the American jurist, who came up with the idea of the balance between public rights and private rights, also known as freedom from, as well as freedom tos. This will allow for the bundle of rights doctrine to survive individual strong privacy protections to allow people to express themselves individually, whilst ensuring community service, preventive maintenance, and emergency response in times of crisis. Next slide, please. Of course, with that being said, Article 2 of the Outer Space Treaty prevents national appropriation by claims of sovereignty by means or use of occupation or by any other means. The treaty, however, does not prevent countries from establishing facilities, but from appropriation of the establishment of those facilities. For example, here on Earth, underneath maritime law, vessels are allowed to operate in international waters. They're still registered to that country, and they've still got sovereignty in that country, but they don't control the waters they operate in. Similarly, satellites in low Earth orbit, under the Outer Space Treaty, are allowed to operate and have sovereignty to that country, although they don't claim rights to that space. So, prima facie, the Mars City would most certainly survive. With that being said, amendments to the Outer Space Treaty, Article 2, to accommodate nationhood powers may be advisable, given the latency between Earth and Mars of optimally 24 minutes, but also longer distances, even where there are solar storms that may disrupt communications. In these situations, if an emergency or similar disaster occurs on Mars, it may be advisable to establish a standing government to allow the Martian population to respond effectively. Next slide, please. The criminal justice system for Mars is difficult to anticipate. Ordinarily, our offense rates are estimated on offenses per 100,000 citizens. That being said, as you may appreciate, we don't have any off-world settlements of 100,000 people. We do have some comparable areas within Earth, such as regional remote urban environments such as acreage in Alaska and Perth in Western Australia, but these still remain relatively close due to transport hubs such as highways, seaports, and airports. Counterwise, research stations in Antarctica, which possess a hostile climate, do not also offer an equivalent experience to Mars, given the fact that these have populations of less than 1,000 people and are primarily made up of government and research scientists. However, we do anticipate that crime will remain a social problem. This may be due to stressing factors or due to mental health considerations. For this end, our intelligence-led policing model will most certainly incorporate strong social and community support to ensure a crime mitigation strategy is effective. Next slide, please. Alongside these considerations of private and public interest and balance, and ensuring people have the ability to express themselves freely as individuals while also cooperating as a community, we'll have strong social and cultural aesthetic regimes in place. As you may appreciate, moving materials from Earth may be difficult. However, we can use a Martian environment to make unique experiences for each individual. Liminal spaces, such as the size of private dwellings, may allow for people to have their own creativity and delineate their space from that of others, such as found in the slide on my right, the image on my right, which is a stencil artwork common in the German graffiti counterculture scene, as well as by Banksy and others. Meanwhile, the slide on my left shows a repurposed Zeppelin dome on the outskirts of Berlin, which is being used to create a tropical environment to allow Berliners to enjoy tropical environments during the course of winter. This is also similar to what may happen with our shared and common community environments on Mars, such as the tops of our domes will be repurposed for different environments. Next slide, please. As you can see, our key learnings have shown that while unknowns still persist with the Martian environment, we know that this is viable. We have demonstrated previously in our literature from last year that a 1,000-person settlement is definitely possible given our current capabilities with engineering. Following from Elon Musk's observations in his yesterday's presentation that an economic case also needs to be made, we can demonstrate through our solarized economy that Mars may become economically viable as it becomes the primary nexus point for an interplanetary economy to thrive. Called a solarized economy, we see this as being a great fusion of collectivism and individualism, and we look forward to seeing you amongst the stars. Thank you for your time.
Time for question and answers. Okay. Kyle, you can ask a question.
Thank you. I wanted to ask you guys about what did you guys consider the how much power it would take to construct the buildings and domes that you guys were considering, and extracting all that regolith and bringing the machines and necessarily to do that sort of excavation operations. Can you talk a little bit about that?
We didn't consider the energy to bring it to Mars, but we did consider the energy it would take to build the city up over that period of time. Over that 60-year period, our energy production there is quite reasonable. In addition to that, to get the amount of steel out of the soil, you would only need to excavate a pit roughly 8 kilometers by 8 kilometers, but only 1 meter deep, so relatively small. Again, over that 60-year period, the energy costs are fairly well distributed. So,
George, your question?
Thank you. So you show the hexagon urban layout of connected colosseums. You have the electrical power going in, you have the heat rejection from the human bodies and the heat rejection from the plants. How do you handle the thermal balance of the colosseums? Have you looked into the engineering of that?
Yes, we did estimate, I don't have the numbers on me here, but we did estimate the heat loss of each Colosseum, and we regulate the temperatures through them dynamically using waste heat from the nuclear reactors stored in our water throughout the Colosseums. They lose heat by design, so it's a more passive system.
Thank you.
Manosis? You can unmute Manosis.
Hello, Team 3. Yes, I have unmuted. How long it will take Team 3 to build the city from day one, that you fly from Earth to Mars, until the end, please? Thank you.
So we didn't consider from day dot. We considered once we'd established an initial 1,000 person pilot site based on similar technologies, just with a smaller design. We estimate it would take a full 60 years to reach the 1 million people mark, but using the same technologies for our smaller site, it could be grown organically. And because our main construction materials are just from the regolith and the air, it can be located pretty much anywhere on the Martian surface, closer to more useful materials like copper, uranium, thorium, and the like. Really, the limiting factor is going to be the energy costs. How big can we make our reactors or solar panels, and how quickly can we get people to the surface?
Alexandros?
Hello, thank you for a very interesting presentation. I have a couple of questions for you. The first is, I was a bit confused when you talked about your education budget, because you mentioned that it would only be for retraining. So does that mean that there won't be children and you won't be educating children? So can you please clarify on that, and what will the education policy for children look like? And the second is, I really like your principle, the social principle of balancing collectivism and individualism. But I wasn't sure how exactly that's kind of embedded within various design parameters. So can you give some examples of how you are actually balancing collectivism and individualism in different aspects of your design? Thank you.
Okay, so in terms of the education, our population modeling predicted that while there would be potentially births on Mars, assuming humans can safely gestate in 30% of Earth's gravity, most of the population is still dominated by immigrants who are, would be over the age of about 20 or 30. As a result, we mainly focused on retraining rather than getting more people to come out from Earth. You can get someone a new job there. There would be budget for schools and kindergartens and education with, a very robust education system to cover that, so that people don't necessarily have to choose between job and children. But just by virtues of demographics, it's mostly geared towards retraining. And sorry, what was your second question?
Collectivism and individualism.
Time is up.
Yeah.
Okay, thank you guys. Thank you very much. Time's up. Next team up, please.